Shut up.
Let's see here.
Oh,
All right. I will begin with a word of prayer. So, Dearly Father, we thank you for this day again. I thank you for this class. Just ask you just bless our work today. Help us to glorify what we do, and just understand a little bit more about Rouche's theorem and all this stuff, Lord. In my prayer, Lord Jesus, amen. So, let me get to it. Rouche's theorem. Says the following: let D be a bounded domain with piecewise smooth boundary partial D, and let F and H be analytic, or you could say, of course, holomorphic on D union its boundary, all right, period. If the modulus of H of Z is less than the modulus of F of Z for Z in the boundary, then F of Z and F of Z plus H of Z have the same number of zeros in D counting multiplicity. All right. So in some sense, this is almost a corollary to the argument principle we talked about in the other last class, I suppose. Let's see here. You could kind of picture this like, if I picture this as, suppose this is, a typical point down here is F of Z. All right, and here's 0. So let's see here. Like if I add H of Z, like this, suppose this is, F of Z plus H of Z. If we have this condition that the magnitude of H of Z is less than F of Z, that's essentially saying if you look at the sum of say that the black plus the red is F of Z plus H of Z, it's essentially saying that you can never get closer to the origin. You can never cross the origin. You never can get back to where F of Z started with H of Z, right? Like the magnitude of H of Z is smaller than the magnitude of F of Z, so you can't double back from where you came in this situation. That's not the proof or anything. It's just saying, give you some kind of idea how to picture it maybe. There's a picture in Saff and Snyder's book about a guy walking a dog. So if you can imagine a guy walking a dog with a 20 feet from a pole, right? And he's got a 10-foot leash. It doesn't matter how many times the dog wraps around him and does all kinds of crazy stuff on the 10-foot leash, right? He can only encircle the pole in the center as many times as the guy walks around the pole in the center, right? So that's somewhat of the intuition for why this is interesting, because then you can think about argument principle, right? So essentially the argument, the angle that's being developed is completely being developed by F. No matter what H does, if it wraps around the guy walking around the angle around the center point isn't going to be increased by the little h. Let me give you the argument here. So let's see here. So there's the proof. So we have modulus of h of z less than the modulus of f of z by assumption, right? So that implies that f is non-zero on the boundary of D. Do you see why that's true? If f of z was equal to 0 and you have this condition, it forces what? The smallest modulus of z h of z can be a 0. That would force equality of the moduli of h and f. So therefore, f is non-zero. Okay, so f of z is not equal to 0 for all z in the boundary of D. And so thus, you can pretty easily see this, that f of z plus h of z, right, is not equal to 0 for z in the boundary of D, right? Do you see why that is? Imagine that it was equal to 0. What would that imply? Actually, this isn't really a thus. This is a also.
That they're equal? Or that they have to be equal?
If this was equal to 0, why would that give you a contradiction? Yeah.
Because that would mean the modulus would be, well, I guess if you have h of z equals negative f of z, the modulus would be...
Right. Yeah, exactly. If h of z was equal to minus f of z, then their modulus would be equal, which would contradict the condition. Yeah. Very good. Thus, let's see here. So then observe, for z in the boundary of D, we can write f of z plus h of z, all right, is equal to f of z times 1 plus h of z over f of z. All right? That's reasonable because, of course, we know f of z is not equal to 0, right? Now, what else do we know? Because of this right here, right? What does that tell us? That tells us that the modulus of h of z over f of z is what? Less than 1, right? So what does that tell you about 1 plus h of z over f of z, if you talk about the real part of that? Could it be negative? Think about this. It can't be negative because the real part, right? If the real part was minus 2, for example, that would be a problem over here, right? Because remember, the real and imaginary parts of a complex value are less than or equal to the modulus of the complex value. So at most, the real part could just be a little bit less than 1. It can't be more than 1, which means in magnitude it can't be a negative number larger than 1. So 1 plus this definitely is, greater than 0, right? I mean, okay, it could be minus 0.999, whatever, but it can't be negative. It can't be 0 either, right? You guys with me? So then what? If we think about the argument of f of z plus h of z, right? Well, that's going to be the argument of f of z times 1 plus h of z over f of z. But by properties of the argument, remember that the argument of a product is the sum of the arguments, yeah? Everybody with me so far? So then, if we think about the curve in question here, right? If we think about my bounded, my D with the boundary counterclockwise, right? And I integrate, the differential of the argument of f of z plus h of z, right? It's going to be equal to the integral of the differential of the argument of f of z around the boundary. Why is that? Because this right here, so right here you can just use inverse tangent. What's the word here? Inverse tangent provides, potential. What's the word? Antiderivative, maybe? On the whole loop. Because the values of 1 plus h of z, f of z, they're all in the right half plane. So I can calculate the argument of that by inverse tangent. And if I add up the values of inverse tangent going all the way around the loop, I don't get anything because I can start where I finish, right? I can't usually do this because typically when I'm integrating something, it's not arranged in such a way such that the values of the function you're integrating stay in just one side of the complex plane. But this is contrived in such a way such that this thing here only has angles coming from quadrants 1 and 4 where we have inverse tangent providing a potential. So anyway, the long story short of it here is that the change in the argument is completely given by that, because this doesn't give you any net change in argument if you go full circle. So then what? Remember argument principle number 2? What did it say? So this is equal to what? The number of zeros, right? Minus the number of poles. And this over here is equal to the number of zeros, right? Minus the number of poles for what? For f of z plus h of z. Sorry, my handwriting gets kind of wacky down here. And this is for f of z. And are there any poles? No, by assumption it's holomorphic, right? So therefore, the number of zeros for f of z plus h of z is equal to the number of zeros for just f of z. Okay, so what's usually done here, to give this thing a name, usually we call this thing the perturbation. Or you might call it a deformation. It's changing f a little bit. So that's Rouche's theorem. So example 1. Example 1 here. Stick with my notes because Ernesto and Preston broke my brain earlier, so I'm still recovering. P of z is z to the 11th power plus 12 z to the 7th power minus 3z squared plus z plus 2 on the unit circle. So what I want to do, I want to consider this thing, that polynomial on the unit circle. And I want to argue that we can see, in fact, that there are 7 zeros in the unit circle. Now, first of all, do you want to factor this? Let me just point out, we do not want to factor it. And naively, you might expect that that 11th power is more important, right? From your previous experience. Like, that's my previous experience, is like the biggest power on the block is like the boss of the algebra, you know? But that's not the case here, actually. So what we're going to do is we're going to look at, well, let me just, basically all of this stuff right here, that I'm going to think of as my h of z, and the other piece will be my f of z. So that's nice, because how many zeros does, you know, if I let f of z equals to 12z to the 7, this has what? 7 zeros on modulus of z less than or equal to 1, right? In particular, it has z not equal to 0 with multiplicity 7, right? So that's easy. We can see that basically for free. And then h of z, we're going to define to be z to the 11th power minus 3z squared plus z plus 2. You guys on board with me here so far? And what condition do we need? So first of all, obviously holomorphic, right? And so what do I need? I need to check that the modulus of h is less than the modulus of f on the boundary of the unit disk, right? So I need to look at modulus of z equals to 1, right? And let's see here. So modulus of f of z is equal to what? Well, 12, right? 12 times modulus of z to the 7th power, but that's just straight up 12. What's the modulus of h of z equal to? Well, it's less than or equal to the modulus of z to the 11th plus the modulus of minus 3z squared plus the modulus of z plus the modulus of 2. I was very dumb and I just applied the triangle inequality repeatedly, right? But we can do better, right? Sorry, I seem to have said do better in my class. I apologize for that. Whenever I say do better, it makes me feel a little less human. But anyway, that of course is modulus of z to the 11th, and that is 3 times the modulus of z squared, and that's modulus of z, and that's 2. But I mean, let's not be dumb. Modulus of z is equal to what? 1. So that's actually 1 plus 3 plus 1 plus 2, also known as 7, right? So apparently, the modulus of h of z is equal to 7, which of course is less than 12, which is equal to the modulus of f of z in this case. Now, modulus of h is not equal to 7, it's what? I should less than or equal to, but that's all I need. So therefore, by Rouche's theorem, the number of zeros that p of z has within the unit disk is 7. I don't know what they are, right? But they're in there. Yeah? So how many zeros does this polynomial have outside the unit disk? 4. How do we know that? We proved the what?
Polynomial of degree 11.
Yeah, the fundamental, because you're about to say the fundamental theorem of algebra, right?
Oh, I wasn't going to say that.
But you
I
were.
was going to say it's polynomial degree of 11.
It's a polynomial of degree 11, therefore it has 11 zeros, possibly repeated, possibly complex. Well, definitely complex. I mean, what else would we do? But that is the fundamental theorem of algebra. That a polynomial over the complexes has n zeros, possibly repeated. Okay? Actually, a little bit out of order from the notes, but let's prove that. So fundamental theorem of algebra, right? Given P of z is equal an z to the n plus an minus 1 z to the n minus 1 plus da 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 plus a2z squared plus a1z plus a sub 0, where what? You know, an all the way on through a1 through a0 are complex numbers, and a sub n is not equal to 0, right? Then P of z has n zeros on the complex plane, counting multiplicity. And then, since we know the factor theorem, we know that also means that we could factor it as a sub n times z minus z1 times z minus z2 times z minus z3 da 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 z minus zn, right? If you know this, if you know there are n zeros, then you know you can apply the factor theorem n-fold times, and so whatever your favorite form of the fundamental theorem of algebra is, you can get to it. Now, some people's form of the fundamental theorem of algebra is just that there exists a 0 for an nth order polynomial. See, because if you get 1, then you can split it into n times n minus 1, and then you can apply the theorem again and again and again and again. But I kind of like this version. And so what are we going to do? We're going to prove this by Rouche's theorem.
You have to find a radius that is sufficiently large. And we have to show that that polynomial is less than a different function.
Right.
You just said there's 11 zeros and 7 are in the unit circle.
Well, that would be fine for example 1, but now we're order n. Right? We're order n now. So how about this? Let's let f of z equal an z to the n, right? Hence, you know, f has n-fold zeros, n-fold 0, let's say z naught equals to 0, you know, on any disk modulus of z less than or equal to r, right? Any r you like, that has n zeros at 0. That's it. There's no other zeros other than 0. We can all agree, right? You can't have n plus 1 zeros, for example, for a degree n polynomial. That brings in chaos, because then you apply the factor theorem and you get your nth order polynomial is n plus 1th order. That would be bad. That'd be very embarrassing. Can't do that. So definitely there's only n zeros for this. We all agree. You're like, okay, that's the really trivial part. You don't need to belabor it. Fine, fair enough. Fair enough. Well, let's let h of z equal to the rest of it. All right. Now we gotta get control of this thing, right? So first of all, you know, let's keep our eyes on the prize here. What is the modulus of f of z on the boundary of the disk of radius r? Let's keep that right. Ah, come on. Really, man, that was really on there. The modulus of f of z is literally the modulus of an times r to the n on modulus of z equals to r, right? So if this is my d, this is z in the boundary of d, right? So that's what we're up against. Okay, we gotta be careful to. Razzmatazz skiddly doo? What's that all about? Kind of crazy nonsense is they're talking about? See here. Look, so if I'm assuming, let us assume that the modulus of z is equal to r, then triangle inequality, let me just cut to the point here, is r to the n minus 1 plus plus a2 r squared. My bad. These are complex coefficients. You can't just leave those outside. We have to take the modulus of them, right? So modulus of a2 r squared plus the modulus of a1 times r plus the modulus of a sub 0, right? And we want that to be less than, excuse me. So I don't know, we can be super greedy, let's be like super greedy and stuff here, right? So to start with, let us add on our wish list r greater than 1. Fair enough? R greater than 1, that seems like a reasonable thing to insist on. If we do that, that means that r to the n minus 1 is the biggest thing on the block here, right? So I can rewrite this as less than or equal to the sum of the moduli of the coefficients, right? R to the n minus 1. You guys with me? Not a big move, really, assuming that the radius is larger than 1. And then, how about this? These coefficients are given, right? So, like, this is just some constant k, right? So we could just say that, that's equal to, like, k times r to the n minus 1, just to give this a name. Just calling it k, some name calling. And then, how about m? Let m be the max of k and the modulus of a sub n, yeah? Then this is, do I have the max or the min? I think max.
If you're trying to say less than or equal to, you need the max.
Okay, so this is less than or equal to, like, well, I'm sorry. Let me think for a second here. I don't have these details in my notes. I'm just like, it's clear. All right, like so many people do. Well, it's true. Obviously, right? But we're trying to come up with some kind of convincing thing that this is less than the modulus of f of z, right? Which is a sub n r to the n, right? And we definitely have something to work with here, because this has an r to the n minus 1, whereas this has an r to the n, right? So intuitively speaking, if you just think about r getting super huge, like whatever happens with these coefficients, it's whatever, But just to be clear,
if r is greater than k over modulus of a sub n, please.
You say r is greater than what?
K over modulus of a sub n.
That would give me what? That would give me a sub n. That would give me this? Actually, that would give me this, right? Is that what you're saying?
Yeah.
Right, and if it's...
And the inequality would be, or on the inequality would be strict.
Yeah, let's make this strict, so we get a strict inequality here. So apparently we just need to do what? We just need to choose r equal to the max of like 1 and this, k over the absolute value of a sub n. And if we do choose that r, for that r, we have that the modulus of h of z is strictly less than the modulus of f of z on the circle modulus is equal to r. Therefore, the number of zeros for the number of zeros for f of z plus h of z, also known as p of z here, is equal to n by Rouche's theorem. Yes?
If r is equal to k over modulus of a sub n, wouldn't it be equal to
We have control over R, though. We can make R as big as we want.
So it needs to be greater.
Well, I definitely would like, I mean, what I want is K to be less than modulus of A times R, A sub n. Because if I have that, then I can go from here to here, right? So this is the same as saying K over the modulus of A sub n is less than R, aka R is greater than K over modulus of A sub n, which is what we said. I think it's okay.
Yeah, so for the max thing, it would have to be R is greater than.
It does say R is greater than 1.
It says R is equal to.
The max of, oh.
Yeah,
that
it
is
has
true.
to be greater than.
Oh,
Yeah.
there you go. Is that better? I see your point.
Well, no, because if R is equal to the max and 1 is the max, then,
It's just one.
yeah, then wouldn't those be equal to each other?
If I write this, I automatically get that R is greater than or equal to 1 and R is greater than or equal to K over modulus of A sub n plus 1, which of course is greater than K over modulus of A sub n, which gives me what I wanted, which was that R is greater than K over modulus of A sub n. Or equal to 1, but it's also, if it's the max of these two things, you get both at once. It's a twofer. This is the joy of jerry-rigging these sorts of things with the max, is you get both conditions at once. And it's just like those epsilon delta arguments we made in Calc 1, where we choose like the minimum of the like 1 and the epsilon over whatever, so we get both conditions at once. Same kind of idea. Anyway, the larger point here, so I had the good sense to not go through all these details in the notes, right? I just say it's clear you can make R sufficiently large so that the magnitude of the leading term in the polynomial completely dwarfs the magnitude of the rest of them, right? Which just intuitively speaking makes a lot of sense, because if you had like radius 1,000, right, and you're talking about a third order polynomial, well the top term is like 1 billion in magnitude, but the next to leading term, the quadratic, is only what? 1,000 squared, 1 million, right? And 1 billion is much bigger than 1 million. You'd have to have very large coefficients to make up the difference. And then of course you can just repeat the story instead of at 1 million, instead of at 1 billion at a googolplex or whatever, right? So always the leading term completely dwarfs the lower order terms in these kind of arguments. Anyway, by Rouche's theorem, we have it. It's proof, fundamental theorem of algebra. I would like to point out there is a fundamental difference, logically speaking, between this argument and all the other ones we've given, which is what? What kind of proof is this?
Proof by example?
Proof by example. Proof by example.
Well,
How
yeah, right?
dare you? It's proof. It is a direct proof,
Oh.
right? I've directly applied Rouche's theorem. Proof by example.
Well, isn't it an example?
You hurt-
Everything's set.
You hurt me with that.
Proof by plugging 3 numbers in.
Ironically, interestingly enough, plugging 3 numbers in a particular order and prescribing 3 places that they must go is actually how to define the next thing we're talking about. So,
Let's go.
good for you. So anyway, I'm gonna stick a fork in this one. It's done.
Wait, are we still going to be talking about Rouche's theorem?
Oh, I do have one more example if you'd like to see it. That's true. I do have one more example. You want me to do it?
Yeah.
All
I
right.
was going to ask about one where it's not the unit circle.
Oh, sure.
You have,
Like a half plane.
not a half plane.
Ah.
It's a z naught that's not 0. Like it's not centered around
Modulus of z minus 12 is less than
So, the setup for Rouche's theorem is for a bounded domain, but you can use it on unbounded domains if you play your cards right. Basically, you just take, if you can basically make the argument for an arbitrary bounded domain, and then you take the limit as the size of it gets bigger and bigger, then you can kind of like cover a half plane, for example. This one isn't based on 0, so I guess it's a good example for you guys. So let's see here, example, what am I on? This was example 3. So, I mean, I guess this was an example, huh?
That's our example.
This is example 2? There we go.
But am I wrong though? Because those are all set. That's a set polynomial. Oh wait, no, it's an arbitrary.
It's an arbitrary one. Yeah. Example 3. Ah. Ah.
Dang it.
Man. Finally. All right. All right, here we go. So z plus 3 plus 2e to the z equals to 0 is an equation we can look at. And the claim is that this has precisely one solution in the left half plane. So what do I mean by left half plane? So if this is my, imaginary axis, we're talking about the real part of z being less than 0, less than or equal to 0, I suppose, right? And so the basic idea here, I guess I should explain, let's just think about this 2e to the z term. What is it? It is 2e to the x plus iy, right? Which is what? 2e to the x, e to the iy, right? So think about how that works. That is going to be what? What's the modulus of this?
Less than equal to 2.
Yeah, it's 2e to the x, right? So you say it's less than or equal to 2? But e to the x can be huge. What's the context, though? Left half plane. So we're over here. Right? Yeah, x is less than 0. So what we want to do now, but the thing is, I can't apply Rouche's theorem. I can't really apply Rouche's theorem to the left half plane, right? So in my notes, I used like, I think I used a half circle. It occurs to me, we could just use like a rectangle. Want to do that? I mean, it doesn't really matter. We need a bounded domain though to hang our hat on. So this is like IR and minus IR. And let's just go like over here and over there like that. So this is my domain. And how do you guys want to define these corners over here?
Wouldn't it be IR minus R?
IR minus R and minus IR minus R. So you chose a square, correct? You don't know.
I don't know what's going on.
But you just told me what to do. How can you not know what's going on?
But yeah, that would work, right? Because R is going to go to infinity and we're just trying to get negative infinity. Ooh, that wouldn't work, would it? Because it'd be infinity minus infinity.
Is that the problem?
Oh wait, no, it would work. I don't know. Maybe infinity times I minus 1.
let's try this out, and if it blows up in our face, then we'll tuck our tail between our legs and go back to the notes and use the half circle that I used there. Okay, but I'm gonna try this. Is my region D, and the thing is, what I'm going to be thinking about is my f of z, right, is z plus 3, and my h of z, my perturbation, is 2e to the z, right? And by the argument, notice that we have modulus of h of z is what? It is less than or equal to 2. And that's just for x less than or equal to 0, right? The question is, what happens with f of z? I guess, I think I understand now. What's the annoying part? We have to do what? We have to analyze the, where does the condition, I've erased, I haven't erased it. Notice that the condition for Rouche's theorem, it's not through the bulk of the region, it's on the boundary, right? So if I'm going to check on the boundary of D, if I do this, I've got four cases to check. But they're 4 easy cases, right? So like here, you've got what? You've got Z equals to IY. Here you've got what? Z is equal to X plus IR. Down here, you've got Z is equal to X minus IR. Over here, you've got Z is equal to what? Minus R plus IY, right? In both of these, we're talking about minus R less than or equal to X comma Y less than or equal to R by construction, right? That's what we have to consider for the modulus of f of z. So what's the modulus of f of z then? It's the modulus of X plus IY plus 3, right? I guess I should give these things some labels if I'm going to do it this way. See, the reason that the notes are slightly slicker is because by doing a vertical line segment and a half circle, you've got 2 cases rather than 4. You know? 1, 2, 3, 4 cases comprise the boundary here. So case number 1, what's the modulus of f of, well, IY? That's equal to what? Modulus of IY plus 3. And what is that range over? Well, let's see here. What's the biggest? What is the biggest that h of the modulus of h of z can be? Is 2, right? What is the smallest? What is the smallest that this can be? 0. Whoa.
I think it'd be greater than or equal to 0. Well, not greater than 0.
Has to be at least 3.
Oh, yeah, I need to, yeah, you're right. I better, what should I do? I need to assume that R is greater than 3, right? For this argument to work. Because if R equals to 3, then like minus 3 is on the left leg, which would violate the terms and conditions of Rouche's theorem. So I need to have the square bigger than 3. I guess it's not a square either. It's a rectangle, isn't it? So you're right, Anthony. Because it goes plus or minus R, but it only goes 1 R over. It's a rectangle, right? It's going from 0 to minus R in the horizontal. It's going from minus R to R in the vertical. It's a rectangle.
It is a rectangle?
Uh-huh. Not as I've drawn it, but.
I was just thinking we need a minus infinity from it. Because isn't that what we're going to do?
We're just going to do a minus infinity? I don't know what that means.
Are we going to take the limit as R goes to infinity?
Yeah. Well, we'd like to show that we'd like to show that Rouche's theorem applies on on this rectangle of side length r / 2r for arbitrary r greater than 3, because if we can do that, we're good. See, how many zeros does f of z have on the left half plane? Just one at -3, right? -3, that's it, just that 1 0. So if we can show that this perturbation satisfies the needed conditions, then we can apply Rouche's theorem, and then we just let the size of the rectangle get as big as we like. We get the whole half plane. So I think that's what you meant. All right, so this here, did I do it right? X equals to 0 on 1, y is y, and y is ranging from, you know, wait a minute. I'm sorry, I'm confused. Oh. Oh. Well, I'm a dummy. What is this? I'm thinking that these cancel, because I'm thinking like, oh, well, y is -3, then these cancel, which is just moronic. What's this equal to?
Greater than or equal to 3.
I mean, what is this equal to? This is the square root of 9 plus y squared, right? Which is what? Greater than or equal to 3. So it's certainly not smaller than 3, which means it can't even get to 2, which is a you know, upper bound for the modulus of h of z. Sorry it's taken me so long to say this. It's actually very obvious if you're just not an idiot about inequalities like I am. So 2 modulus of f of, in the case 2, we've got what? X plus IR, which is, let's see here, so we've got X plus IR plus 3, which is the square root of X plus 3 squared plus R squared. Maybe that's why this doesn't work.
Isn't it just greater than 3 plus r?
That has to be greater than or equal to r, which is in turn greater than 3 by assumption.
So this is greater than or equal to R, which is by assumption greater than 3, which is greater than 2, which is greater than or equal to, all right. Cool. And in fact, you know, why don't I just go ahead and put us out of our misery, slap a minus up in here, plus or minus R, because this will also work for case 4, right? And then case what? What's the case that's left? Case 3. We got modulus of f of minus R plus IY, which of course is modulus of X minus R plus IY plus 3, which is the square root of, goodness gracious, 3 minus R plus X squared plus Y squared, I guess. Maybe this is where we get into trouble finally.
We have to adjust our condition to r greater than 5 for the left side.
You think this is R greater than 5?
Yeah.
And why would you say that?
Because that makes that that modulus strictly greater than 2, which is what we need.
Should I multiply this out or something to see it better, or? What do you think? Or you just see it? You just see it. Oh, let me try to understand what you're saying. So, oh, okay.
There shouldn't be an x, I don't think, in f of
Yeah, where'd that x come from?
circle, so
What is x equal to here? X is minus r here, right? So that's part of my problem. So let's fix that. So 3 minus r squared. Come on. Plus y squared. Now you said, now the y ranges from what? From minus r to r. So why do you say, I'm trying to see why you said r is 5.
y could be 0. So to guarantee
Oh,
that
okay.
modulus is at least 2.
Perfect, very good.
Greater than 2, we need r to be strictly 0.
Excellent. So that could be 0. So we need this to be greater than 2. So we should make, so that this will be greater than, so I guess it's greater than 2, which is greater than or equal to modulus of h of z, provided we insist that r is greater than 3. I'm an idiot. R is greater than 5, which then would make 3 minus r greater than, well,
3 minus r squared.
yeah, 3 minus r squared.
The square root of 3 minus r squared.
Well, anyway, we could say this 3 minus r squared is greater than 4, right? Anyway, it is clear what he's saying, that if r is greater than 5, then we have this is greater than 2. So what's interesting is if you look in my notes, I think we also came to the conclusion for the circle that the radius had to be larger than 5. But it's a rather different argument, but isn't that funny? Yeah, if you look, in fact, I just pull it out of my hat at the start of it. I'm just like, where do I say it? Somewhere in the middle, somewhere at the start of the example, I say, in particular, assume r is greater than 5. It's not been motivated, and then as you go on, you see the necessity of it when you get to a particular point in the argument. But here, it's pretty clear. Actually, I think that this method of argument is easier than what's in my notes in some sense. It's a little bit more like, what's the word? Tedious, but it's actually, once you get your bearings, pretty simple to make these arguments. And so let's collect our thoughts. What have we proved? We've proved that the modulus of f of z is what? The modulus of f of z is less than the modulus of h of z for all z in the boundary of, d, let me call it d sub r, for r greater than 5, right? So by Rouche's theorem, the number of zeros for f of z plus h of z is the same as the number of zeros for f of z. But the number of zeros for f of z is clearly 1 because you just have z equals to minus 3. Consequently, there's only one solution to this equation on the left half plane. Does that make sense? I hope it makes sense. So, yeah. Now, it doesn't tell you what the 0 is, does it? It's there, it's somewhere. Where is it, though? I don't know. Can you guys see what the solution is? I don't know. I think that might be one of those ones you need like the Lambert W function or some such nonsense. Do you guys know about the Lambert W function? Oh, somebody does. Okay, good. Anyway, it's kind of a funny thing if you start thinking about it. What we think of as a function and what we think of as quote unquote not a function, it's really, in some sense, just a historical artifact of things people have thought about before. Because you could write down power series other than the ones we've commonly study, and you could give those names and make those elementary functions, and then those would be examples, but we don't. I mean, there is a certain naturalness to sine and cosine, right? You can define them in ways which are not just that, like, what I'm trying to say is there are reasons that the elementary functions are so central to our thinking. Can I erase? We good? Okay. So next up, we are talking about so-called Mobius transformations. Yeah. not Morpheus, Mobius. Not trying to get you guys to take any kind of pills or anything. Let's see here. What's that?
You don't know what's you didn't watch Flatland and Flatland Squared?
Classic math literature?
Have I watched the Flatland? Not really. I know. I'm sorry. I'm such a.
Dr. Sprano put it on.
We got that.
So Mobius transformations. AKA FLT, which is fractional linear transformation. Now, these are actually very, very interesting. And I suppose I probably should start with a definition. So here it is. Given A, B, C, D in the complex number system, such that AD minus BC is not equal to 0. All right. We define the fractional linear transformation to be f of z is az plus b over cz plus d. Now, we'll find it convenient to actually think of them as mappings on the extended complex plane. So actually we'll think of f as a mapping C union infinity. All right. C union infinity. Okay. And okay, so like try to be careful here. What would we say about infinity? How would we define infinity? So here's the deal. This is obviously good for what? For z and c, right? That's how we define the mapping for z and c. How would I define it at infinity? Well, it's a little bit more nuanced, but here's the deal. If c is equal to 0, then f is said to be affine. And by the way, sorry, we're outside of the scope of my typed notes. All right. We're beyond where I've typed stuff for. My apologies. But if c is equal to 0, then f is said to be affine. And where should infinity go? Well, f of infinity is just equal to infinity. All right? But on the other hand, if c is not equal to 0, then what should